Chemical formulas, how to represent compounds with polyatomic ions. Some chemical formulas have groups of atoms that act as a unit. We call these polyatomic ions. Polyatomic. Poly is a prefix that means many, and atomic refers to atoms. So this is an ion with many atoms in it. If we have two or more of these in the same formula, then we use parentheses around them and put the number of units on the outside of the parentheses. So let's look at an example. So here we have, right here in the middle, MgNO3 2. So this is the nitrate ion. This is a polyatomic ion, NO3 minus. That was one of the things that was on the memorization list. That's NO3. So this is a little bit like something you might buy at Costco. You buy an Xbox or a Wii system at Costco, and you get these other things, and they're bundled together, right? You can't just buy the Xbox. You have to get the 2 controllers and the 3 games or whatever the thing is, and they're shrink wrapped together. So the parentheses are a little bit like the shrink wrap, because this is a unit. NO3 is a unit, and the shrink wrap goes on the outside of it, and this number disappeared. This number on the outside of the parentheses tells us how many groups, how many bundle packs we have. So that's what the parentheses mean. So if we're looking at a question like this, determine the number of each type of atom in MgNO3 2. So what are the elements in this compound? We've got magnesium, right? If you guys don't answer the questions, I'll just start talking. And nitrogen, and we've got oxygen. Those are the 3 element symbols that are in this formula. So how many magnesium atoms are there? There's just 1. There's no number after magnesium, and so it's just 1. How about the nitrogen? There are 2, because we have 2 bundle packs. In each package is 1 nitrogen, but there are 2 packages. So we have 2 nitrogens. How many oxygens? 6. Okay, because in each Xbox package, you've got 3 games. So if you buy 2 of the packages, then you have 6 games. Okay, so another way to think of it is it's like the distributive property in math. If you got 2 times the quantity A plus B, we say that the 2 distributes, and you've got 2 of the A's, and you have 2 of the B's. So that parentheses with the 2 on the outside, the 2 multiplies everything on the inside. Any questions? So let's do a couple more examples. Determine the number of each type of atom in the following formulas. K2SO4. Well, first of all, make a list of the different elements. We've got K, S, and O. How many K's are there? 2. How many S's? How many O's? 4. Okay, so in one of these formula units, there's 2 potassium atoms, 1 sulfur atom, and 4 oxygen atoms. How about this one, B, Al2SO43. When you read these formulas out loud, you just say the numbers. If there were 2 numbers together, like one of the reasons that we don't leave those parentheses out, if we didn't have parentheses and we went like that, that would look like there were 43 oxygens and only 1 sulfur, right? And that's not at all what we mean. So when we read this, we just say Al2SO4 3. So we've got 3 elements again, right? Aluminum, sulfur, and oxygen. How many aluminum atoms? How many sulfur atoms? 3. And how many oxygen atoms? 12. Sometimes you might have a lot of atoms of one element, and that's okay. You get large molecules, and they can have hundreds of hydrogen atoms. Any questions? There are different types of chemical formulas. So one kind is an empirical formula, and we're going to talk more about these later. An empirical formula is a formula that's determined by experimentation. So in the lab, you do some experiments and you determine the formula. And it's always going to be the relative numbers of atoms in a compound. The molecular formula actually gives us the formula that tells us how many atoms of each element are in a molecule. The empirical formula is sometimes the same as the molecular formula, but sometimes the molecular formula is a multiple of the empirical formula. So this gives the actual numbers. The empirical formula gives the relative numbers. So an example, hydrogen peroxide is H2O2. In one hydrogen peroxide molecule, there are 2 hydrogen atoms and 1 oxygen atom. If you were to determine that experimentally, the empirical formula would be the relative numbers, the lowest ratio. So it would be just HO. So this is like the ratio 2 to 2, and that can be reduced. That's the same ratio as 1 to 1. So the empirical formula is always the lowest ratio, but the molecular formula gives us the actual amount. And then the structural formula tells us about the structure of the molecule and shows how the atoms are connected to each other. We also have models. Models are just 3-dimensional representations of molecules. And there's different types of those as well. There are ball and stick models. We'll see some pictures of those. We tend to use the same colors to represent the different elements. And you don't have to memorize those. It's just kind of up there because there was a hole there in the slide. And then there are space-filling models, which more approximate the actual shape of a molecule. The ball and stick model is a little like playing with Tinker Toys. And it's a very crude model, and yet it's easy to work with. And we're actually going to do some of that in lab someday. I don't remember what day. So let's look at methane, which has the formula CH4. So here is its molecular formula. This tells us that each molecule has 1 carbon atom and 4 hydrogen atoms. Doesn't tell us how they're connected, though. The structural formula is going to show us how they are connected. And so this is telling us that the carbon atom is bonded to each of these 4 hydrogen atoms. And there are other ways that you could conceivably stick those atoms together, but this is the correct structural formula. This is an example of a ball and stick model, a little bit like Tinker Toys. So we've got the carbon atom in the middle and the hydrogen atoms out here. And this is going to give us more of a 3-dimensional picture. The structural formula is always flat, and so it doesn't really tell us anything spatial. And then the space-filling model. These are really hard to draw, so we'll just leave those up to the computer to generate them. But they can be useful because these are more like what the shape of the molecule actually is. It doesn't actually look like this. But all of these things are helpful for different reasons.